In the quiet stretches of mathematics, there are numbers that refuse to settle. We call them irrational numbers, values defined by decimals that spill out infinitely, never once repeating a pattern. They are the wanderers of the number line. This creates an immediate problem for anyone trying to map them. Take the square root of 50. Because you can't write it as a tidy fraction or a finite decimal, it feels like a ghost. If you can't write down its whole name, it seems impossible to know exactly where it lives. But finding an exact location doesn't require knowing an infinite string of digits. You don't need a number's entire life story. You just need to identify its immediate neighbors, the solid, known numbers standing on its left and its right. Mathematics gives us a precise tool for this: approximation. By systematically squeezing an infinite number between known values, we can prove that even the most chaotic-seeming decimals follow strict rules. The riverbank can be mapped. To catch a wanderer, we start by looking for familiar landmarks, in this case, perfect squares. Because perfect squares have clean whole number roots, they act as permanent, unmoving anchors. We set the trap for the square root of 50 between the closest perfect squares, 49, which is 7 squared, and 64, which is 8 squared. Since 50 is 1 unit away from 49, its root sits right next to the 7. The perfect squares work as a definitive trap. We don't need to calculate the endless decimal of the square root of 50 to know its address. We've locked it into a specific, identifiable neighborhood. This bounding technique can also resolve disputes. Imagine trying to determine which value sits further down the line, the infinite irrational square root of 20 or the short finite decimal 4.4. Directly comparing a neatly packaged decimal to an incalculable root is a guessing game. They are written in different formats, making them difficult to judge side by side. To establish common ground, we square both racers. Squaring the square root of 20 clears the radical, giving exactly 20. 4.4 squared gives 19.36. Since 20 is greater than 19.36, the square root of 20 must be greater than 4.4. Squaring acts as a universal fair equalizer. It strips away formatting differences and translates both values into comparable numbers, letting us fairly judge their placement. Sometimes a whole number neighborhood isn't precise enough. If we need to locate the square root of 8 to the nearest tenth, we have to tighten the trap. 8 falls between perfect squares 4 and 9, trapping its root between integers 2 and 3. Testing tenths, 2.8 squared is 7.84, a lower boundary. 2.9 squared is 8.41, an upper boundary. 8 is closer to 7.84, so the root anchors precisely at 2.8. This iterative method never runs out of room. By continually squaring smaller increments, we can squeeze an irrational number to the hundredths, the thousandths, or any degree of precision the math requires. The strategy for handling these endless decimals relies on a reliable algorithm. Corner the number between perfect squares. Compare competing values by squaring both sides. Systematically tighten the trap by tenths. We boxed the square root of 50 tightly against the 7. We proved the square root of 20 outpaces 4.4. And we locked the square root of 8 down to 2.8. The fear of infinite, non-repeating decimals comes from the assumption that they cannot be controlled. But once you apply strict boundaries, that chaos organizes into a clear, predictable sequence. The mathematical term irrational merely means a number lacks a fractional representation. It means the number is endlessly complex to write down. It never means the number is lost. Armed with approximation, the entire number line becomes fully mappable territory. No matter how wildly the decimal wanders, every value on the riverbank has a precise, readable, and permanent address.